All right, let me join the other first few speakers in thanking the organizers for giving me the opportunity to talk here in this beautiful venue. So I'm going to talk about a relatively elaborate subject, Moonshine, and the way it's evolved most recently to involve three distinct, interesting classes of objects in mathematics: the sporadic finite groups, modular functions and forms, which we're very familiar with in string theory, and then Calabi-Yau compactifications, which also have featured prominently in past strings conferences. Now, I'll be summarizing work of a large number of people, even going back to the 80s, so my role here is very small, but to the extent that I say something new, it will be based on a paper that actually appeared this morning with two gifted postdocs at Stanford, Dong and Race, and three, I don't know, 2.5 mathematicians and half a physicist, Miranda Cheng, John Duncan, and Jeff Harvey, who are experts on the subject. So the talk will be organized in 3 short sections. I myself barely remembered what Moonshine was 2 years ago, and so I'm going to begin by reviewing what this means. I'm going to talk about what brought me back to the subject, which is the entrance of K3 and its BPS spectrum into this story, which goes back much further. And then at the end, assuming I don't use up all my time in the review, I'll talk about string duality, Calabi-Yau threefolds, and modular forms, and how they tie together with these earlier results. So much of the talk will be review, but some of quite recent material. Okay, so what's Monstrous Moonshine? So Moonshine is, it's sort of an enigmatic name. It's called Moonshine because it's a mysterious relationship between natural objects from 2 very distinct realms of mathematics, the theory of finite groups and the theory of modular forms. Now, by roughly 1980, I'll be approximate with dates, the classification of simple finite groups was actually in sight and being completed, and I'm told it's done. So in the final result, which is apparently so complicated that no single mathematician really knows the whole proof, there are 18 infinite series of these groups, and also 26 oddballs, the 26 sporadic groups. And the last and largest of these oddballs, the Fisher-Grease monster, was just being discovered and explored in the early 1980s, right before the anomaly cancellation. So here's the list of the sporadic groups. These lines indicate who's embedded in whom, and the star of the first introductory part of my talk will be this largest one, the monster, whose order is almost 10 to the 54. And then later we'll reduce our ambition, we'll go down to something a couple of levels down, M24, whose order is 244,823,040. So there's a typo there. Now, the monster is huge, so it's amazing that people were able to construct this thing explicitly. Its first non-trivial representation occurs in dimension 196,883, so unlike rotation groups of polygons, I can't draw a picture for you to visualize. John McKay noticed something very interesting, a coincidence, when he was taking a break from his work on this subject to read number theory papers. So let's recall the definition of modular functions and forms. We're used to the idea that we should work in the upper half plane, modulo the action of SL2Z, so here A, B, C, and D have to satisfy AD minus BC is 1, and then quotienting the upper half plane by that action, you get the fundamental domain, the familiar keyhole region from one-loop string theory. So a modular function is one that transforms in this way under such an SL2Z quotient, while forms are allowed to have a power of C tau plus D under such a transformation, and K is called the weight of the modular form. Now, these beasts pop up everywhere in string theory for really 2 different reasons. The first is that the world sheet is a 2D conformal field theory. It should be modular invariant. Large gauge transformations on a torus shouldn't change results in world sheet computations. And so modular functions or forms show up in integrands of string world sheet amplitudes. But also, starting in the mid-90s, we realized that space-time moduli, like the dilaton in type 2B string theory and its axion partner, can transform under strong weak coupling duality symmetries, SL2Z groups, now in space-time. And then the fields take values in this keyhole region, and S-duality imposes constraints on effective actions as a function of those fields. Okay, so here's just a picture of the avatar of SL2Z in world sheet partition functions. You compute the trace of Q to the L naught, and you end up with some nice modular form. Now, a basic result says that any modular function under SL2Z can be written as a rational function of the J function, whose Q expansion, where Q is the exponential of tau, starts out like this. And for most purposes, I should have subtracted off the 744. There's an equivalent definition with large j and no constant term. Now, these coefficients get big pretty fast. And what McKay noticed was the following coincidence. The first interesting coefficient here, this is a normalization, and I can remove this, is almost the same as the dimension of the first non-trivial representation of the monster. And in fact, the second number here, which is even bigger, is easily represented as the sum of dimensions of the first two irreps of the monster, other than the trivial rep. Now, these numbers are large enough that this result would, if we were experimentalists, indicate a coincidence to many significant figures. Okay, so there's a 5 sigma chance that something interesting is happening. Now, this is a long story, but the natural question when you notice such a coincidence, okay, is why is this happening? Why should these objects be related in any way? And at some level, you can answer this why question as follows. There is a two-dimensional field theory related to the bosonic string on an orbifold of the so-called Leech lattice. The Leech lattice is the lattice that you get if you try to pack spheres as densely as possible in 24 dimensions. And 24 is coincidentally the number of light cone dimensions of the bosonic string. So if you put bosonic strings on this Leech lattice, or more precisely, its Z2 orbifold, and if you compute their partition function, you find a modular function, you just Q expand, Q to the L naught, and in fact that partition function is J of tau. So modular invariance gives you naturally, in this 2D field theory, J of tau, and at each level of L naught, the reason the monster is acting, in this theory, is because this conformal field theory, the Z2 orbifold of strings on the Leech lattice, also has a monster symmetry. The Leech lattice itself has a slightly smaller symmetry, the so-called Conway 1 group, that was also in my table, but the orbifolding enhances it to the monster. So this is a very pretty explanation. There's a field theory, it has monster symmetry, and so its partition function organizes states by mass and in terms of irreps of the monster. And you know, many mathematicians and physicists played a role in elucidating this. Now, given this field theory, if we compute the partition function, we could also choose to do something we do in studying orbifolds. We could impose boundary conditions on the spatial circle on the world sheet that twist by an element of the symmetry group. So the fields could come back to G action times themselves. So here, for instance, you could have G on the circle and 1 in the time direction when computing the partition sum. Now, when you act with a modular transformation, of course, the boundary conditions get all mixed up. But you should still get a modular form in this physical theory for any subgroup of the SL2Z that preserves the form of the boundary condition, where this final boundary condition turns out to be the same as the other one because of coincidences in the group actions. So if you do twist by G in this direction and 1 in that, you get something that mathematicians call the McKay-Thompson series. You decompose each L naught eigenvalue in the Hilbert space in terms of monster reps, and then instead of having the J function appear when you compute the partition function, you get characters of representations of G, of the monster, evaluated on this group element G that you've twisted by. And because of the argument here, a check on your decomposition in terms of monster reps is that these objects, these McKay-Thompson series, should themselves be modular under some subgroup of SL2Z. So for each conjugacy class in M, it's a conjugacy class because there's a trace involved here, you get such a series, and so there are 194 conjugacy classes. Now, the fact that these are modular with the expected properties was strong evidence for the conjecture even before the bosonic CFT was constructed. And in fact, it could have been checked given your guess for the decomposition in terms of monster reps, even if you hadn't gone and constructed the explicit CFT. So it could be checked beforehand. The lesson is that when a modular form with suggestive coefficients appears, you should check these twisted partition functions, which I'll call twining genera to respect the notation in the literature, also to really convince yourself that some kind of moonshine is at work. I mean, of course, as physicists, these numbers are convincing enough, but mathematicians have psychological problems with that. Okay, now while this story relating monstrous moonshine to some particular 2D CFT is a beautiful story to be sure, it's also seemed, at least to me, somewhat of a peculiarity, something off on the side, away from the main action in string theory. This changed to some extent in 2010, when K3 entered the story. So K3 serves as the simplest non-trivial example of Calabi-Yau compactification, And it's also played a central role in many of the string dualities that relate, for instance, M theory to the heterotic string since the mid-1990s. And I don't need to tell you what fraction of talks at these conferences have involved one of those two subjects. Now, the K3 sigma model, is a highly non-trivial, two-dimensional 4,4 supersymmetric theory. It's not a theory that you can solve in any easy way, but as we just heard in previous talks, index information or cohomology of supercharges can be useful when the theory cannot be solved. So the most famous example of this, of course, is the Witten index in a theory that has at least one interesting supercharge, as in the last talk, some linear combination of the Q's that has the right squaring to make Hodge theory apply. All excited states in the supersymmetric theory come in Bose-Fermi pairs, but ground states need not be paired. On the other hand, as you move in parameter space in the theory, if the ground states are to be lifted, they must move up or down in energy in pairs. And therefore, the trace of -1 to the f gets only contributions from this lowest level, and it's an invariant, which in this case would be called the Witten index. The hero of the part of our story I'm telling now is going to be a more refined version of that Witten index that can be defined in two-dimensional theories, like a K3 sigma model, that have at least 0,2 supersymmetry in 2 dimensions. And this is something called the elliptic genus. So let's assume that the left movers and right movers both enjoy n equals 2 SUSY. I'm specializing more than this for the exposition. The n equals 2 algebra, say on the right, requires that Q right with plus U1 charge of the n equals 2 algebra, commuted with Q right of the minus charge of the n equals 2, commute to the Hamiltonian. And so the one-loop partition function would naturally be written as a trace on the Hilbert space of Q to the H on the left, Q to the H on the right, and then some parameters gamma that measure the U1 charges. Now, the n equals 2 algebra, like Virasoro, has highest weight representations, and so we could list the highest weight representations that are present in a given conformal field theory. Let's say they run over R alpha and R bar alpha, just for simplicity, for the left and right n equals 2s. So then we could write out the partition function that I just mentioned in this way, as traces over the right and left Hilbert spaces. But except in very, very special CFTs, orbifolds, or Gepner points or something, we actually can't solve for this full partition function. So you can write this, but it's not of much practical use. If you could solve for it, it would contain, for instance, the full spectrum of the space-time theory, including alpha prime corrections, though not G-string corrections. So what we do instead is we sacrifice some information to instead get an index that will be computable. Now, if we went all the way back to the old Witten index, that would correspond to dropping all information about U1 charges in this partition function. Okay, and there's not a lot of information there. But we can consider setting only, say, the right moving U1 twist to 0, so that the right moving bit in our sum becomes a trace over the right moving representations of -1 to the f q bar to the h, which is roughly a right moving Witten index. I'm being a little heuristic here. So then you get contributions only from right moving ground states, and there's a non-trivial modular form coming from the levels on the left. Okay. And a similar elliptic genus can be defined for theories with just only the right moving n equals 2, but I won't go through it again. So the function that we can compute now has a Q expansion and is a function of one other variable to tabulate the left moving U1 charge. So this is clearly a more refined sounding invariant than the Witten index because it has a nice Q expansion. In the K3 sigma model, it turns out that in space-time, for reasons I'm not going to go over here, but they should be very plausible, the elliptic genus counts a weighted sum of space-time BPS states, which arise, for instance, in type 2a string compactification to 6 dimensions on K3. It was computed, actually, now 24 years ago by these authors. So here is their notation, Q to the L naught, Y to the JL. So those are the two variables. And the result they found was some nice sum of 8 times the sum of Jacobi theta functions. So these Jacobi theta functions, for those of you who are like me, you can look up in Wikipedia. Now, representations of the n equals 4 worldsheet algebra are labeled by two numbers, a conformal spin h, that is the L naught value, and the n equals 4 algebra has an SU2R symmetry. So there's an SU2R J3, which we could call L. So then it's natural to expand the partition function, or the elliptic genus, in terms of multiplets of the remaining n equals 4 in the computation. And doing this, what the authors found was that there's a nice sum over the characters of the massive BPS representations, each appearing with a coefficient an. And the coefficients an are, well, there's a 2 times 45, 2 times 231, 2 times 770. And 21 years later, some of the authors, along with Tachikawa, noticed that these numbers and some much larger numbers that appear further down in the list are actually dimensions of irreducible representations of the second group I mentioned at the start, the Mathieu group M24. So this is a sort of twisted BPS version of the Moonshine we started with that related the J function to the monster. It's a slightly smaller group and a slightly more refined object. Now, much further work has elucidated and generalized the conjecture that these authors made. Some of the experts are in the audience. Here's at least a good subset of the people who have further elucidated this conjecture in the last 3 years. But it needs to be emphasized that as yet, there is, unlike the case of the monster, no explicit realization of a physically relevant CFT that really explains the full observation. Okay? And in fact, there's a proof by the group at ETH that no 4,4 sigma model with K3 target can ever admit the full M24 symmetry. Now, I'm not going to try and shed light on that, though maybe light will eventually be shed. I'm going to try to ask a different question, which is, does some evidence of this moonshine persist in vacua of even more interest, at least to me, which are vacua with less supersymmetry? So I'm going to focus on the case, henceforth, of 4-dimensional n equals 2, though we could move back and forth to 6 dimensions in n equals 1. Okay, so how do you get 4-dimensional n equals 2 vacua of string theory? Well, there are 2 simple ways that I know. You can consider heterotic strings compactified on K3 with an extra torus to go along to get to 4 dimensions. Or you can start with type 2 strings, but now use Calabi-Yau threefolds. We lose no generality by talking only about type 2a, because mirror symmetry relates to sets of compactifications. It's a result from the mid-90s that in fact these 2 sets of theories are mapped to one another by duality. The natural data in the heterotic theory would be the following. There are E8 cross E8 gauge fields in that heterotic string in 10 dimensions, and a Bianchi identity for the three-form field strength requires that you turn on a certain number of instantons in gauge bundles V1 and V2 that you embed into the 2 E8s. So for a perturbative heterotic model, the E8s must be broken by embedding these instantons in the gauge group. And the counting is such that you have to distribute 24 instantons in the 2 E8s. Anti-instantons are not allowed because they would break supersymmetry. So that gives some set of models. The dual Calabi-Yau threefolds to these were worked out in full generality in that period. They consist of elliptic fibrations over Hirzebruch surfaces, Fn, and the labels on the Hirzebruch surface map to this combinatorics, such that for the surface Fn, the n1 here is 12 plus n, and the n2 here is 12 minus n. The Hirzebruch surfaces with larger n here don't give smooth enough Calabi-Yaus to use. In this map, also, the dilaton in the heterotic string has a very geometrical role here. It maps to the size of the base P1 of this Hirzebruch surface, which is a P1 bundle over P1. Okay. And all these statements were first derived in precision or generality and can be lifted to 6-dimensional dualities in the F-theory setting. But I'll speak in 4 dimensions. Okay, so there's a big web of such vacua. They have various possible unhiggsed gauge groups depending on how big you make the vector bundles. If you choose an SU2 bundle, E8 breaks only to E7, but you could choose a bigger bundle. And for each gauge group, you can go to the Coulomb branch of the gauge group and get a model where the non-abelian symmetry is broken and so forth, as is familiar in n equals 2 field theory. So dual descriptions of the heterotic non-abelian groups involve some singular Calabi-Yau spaces. There's a diagram of all the groups that you get in this way, and F-theory duals are known for more or less all of them. Now, what are we going to look at to see if there's some notion of moonshine here? Well, a good quantity to look at, sort of analogous to the elliptic genus, is something called the new supersymmetric index of the heterotic conformal field theory. The heterotic string doesn't require both left and right moving supercharges. So the natural supersymmetry in this context is a chiral 0, 4 supersymmetry. And for any such theory, you can define a new supersymmetric index following these people that takes this form. Okay, this is because of the transverse light cone gauge bosons. You don't need to worry about that factor. But this is a trace of j e to the I pi j, q to the L naught, q bar to the L naught bar. More generally, we could have a parameter there. So this quantity is particularly interesting because in old work by Harvey and Moore, there's a discussion, it involves the word moral, but I'll say it here because this is not yet a math conference, that morally, this z nu is a sum over BPS vectors minus BPS hypers. So its Q expansion is some kind of index in the space of BPS states. Now, beyond morals, there are also places it shows up in effective actions that you can compute. For instance, it shows up in the one-loop threshold corrections to the space-time theory, the one-loop corrections to gauge couplings, or to R-squared terms, in the low-energy gravitational action, involve exactly traces that involve the new supersymmetric index, contracted either with the modular form E2, the non-holomorphic modular form E2, or with some gauge matrices that emphasize different E7 or E8 quantum numbers. Now, it follows from the fact that we expect the action to be well-defined, and this kind of form, that this quantity should be modular invariant, okay, with the extra tau 2 to make up for the fact that this is not quite the modular invariant measure. So I'm going to focus on the case of the gravitational threshold. We discussed both. And I'm going to furthermore turn off all Wilson lines. So we're sitting with the maximal space-time symmetry allowed by whatever vector bundles we stuck on the K3 surface. Well, then the index further factorizes. You get some theta function that's basically parameterizing the momenta and windings on the torus in K3 times T2. This is some partition function that you compute once and for all in old textbooks. Here it's given. And then there's still the 1 over eta squared, and there's something I'll call g of K3. And it follows from our desire for a well-defined space-time action that g of K3 over eta to the 4th has a weight which is formally minus 2. Now, using the facts that, first of all, in a heterotic theory, the left movers are a bosonic string, they had a tachyon, so we expect a 1 over q pole in z nu, that this has to come from the interesting part of our computation, because the torus sum has only positive powers, non-negative powers of q appearing. And that then eta to the 20 times gk3 has to be a holomorphic modular form of weight 10. We just multiplied this by eta to the 24th. It follows from all that that this particular combination must appear as g of k3. The ring of modular forms is generated by E4 and E6, and this is the unique thing that can appear there, independent of the choice of the gauge bundles on K3. Now, the normalization, the 1, can be fixed in various simple ways. For instance, there's the famous 6-dimensional gravitational anomaly that constrains the number of hypers, vectors, and tensors in any theory in 6 dimensions with at least 1, 0 supersymmetry. So that fixes the normalization of the form I wrote to be 1. Now, that universal structure contains actually a factor of E6 over eta to the 12th, and then another factor that has to do with the existence of an affine E8 that shows up in this computation. And if you massage g of q in much the same way that EOT massaged the elliptic genus, you'll find that it can be written as a sum over an infinite tower of massive states with coefficients an, where now the sum involves characters of SO12. These are some gauge representation data in the heterotic theory, multiplying n equals 4 characters. And importantly, these coefficients an are exactly the same as they were in the K3 compactification, these dimensions of M24 representations. So a natural question is, how does this modular form manifest itself in the dual Calabi-Yau manifolds? Well, the one-loop threshold corrections that I was just discussing in the heterotic string actually determine the one-loop prepotential. Okay, you can integrate back from the one-loop thresholds to get the one-loop prepotential. Now, in the dual Calabi-Yau compactification, prepotentials are counting holomorphic curves embedded in the Calabi-Yau. There's some quantum cohomology calculation that you do. And the perturbative heterotic limit maps to the limit where you compute this quantum cohomology, or you count curves, when the base of the dual Calabi-Yau is extremely large. That's large volume for the base in type 2. So the universal heterotic degeneracies, if we can understand them in type 2 strings, should be visible in curve counts in a certain limit of type 2a Calabi-Yau compactification. So we actually were able to demonstrate this by making use of recent results in the mathematical physics literature. So building on work of Yamaguchi and Yau, who had argued that topological string theory on one modulus Calabi-Yaus has a set of higher genus FGs, counts of genus G modular curves, that are governed by rings of at most 5 or 6 functions. These two groups were able to show that for elliptic vibrations, the structure becomes more simple and striking. What you do is you expand the genus G prepotential as functions that depend only on the modulus of the elliptic fiber, e to the minus 2 pi tf, times a power series of possible appearances of base moduli. Here I've said B1 and B2 for the sizes of the two curves in the Fn. And it's been shown by these group that these coefficient functions are determined entirely by modular forms in the ring generated by E2, E4, and E6, as is normal, okay, with a weight that's given just by the genus of the FG or after, and some polynomial determined by intersection theory on the Calabi-Yau. Okay, so that's all a mouthful, but this is some true result from these mathematicians. They furthermore satisfy interesting recursion relations, which are descendants of the recursion relations discovered by BCOV. For instance, for the elliptic vibrations over F0, 1, and 2, the relations tell you that these modular functions, their derivative with respect to E2 in the ring is given by lower genus computations. Now in all of this, to check anything I say, we need to compare to a one-loop heterotic computation. So that means only the terms with k equals 0, terms where the base of the vibration appears to the 0th power, there's no e to the minus 2 pi times the dilaton, can be compared, but that's still in fact a large set of terms. So the simplest non-trivial term of interest would be F01 at genus 0. Okay, it would be the term in the Q expansion here with no power of the dilaton in some modular form. It satisfies this equation. And using that together with some universal facts about intersection theory on K3 fibered Calabi-Yau threefolds, which these are, you find that in fact that F01 is exactly QF E4 E6 over eta to the 24th, which is the same modular form that appeared in a totally different computation I was doing of a one-loop integrand in the heterotic string. But here it's appearing not as an integrand of anything, but as a function of space-time moduli in the type 2 model. Now, if you do take the one-loop thresholds I computed and solve a non-trivial differential equation for the heterotic prepotential in the same limit, okay, this was pioneered by these authors in the mid-90s, what you'll actually find is the heterotic prepotential looks like this, where these CMs are precisely the coefficients appearing in the Q expansion of E4, E6. So the integrand actually translates perfectly into an appearance of E4, E6 in the space-time heterotic prepotential. That was all a mouthful. I'm also out of time. So let me just summarize what else we were able to do and end my talk. What I tried to give you is some numerological or modular information that indicates that some kind of moonshine may be occurring much more generally than in compactifications on K3. I emphasized at the start that at least for monstrous moonshine, beyond degeneracies, checking twining genera was important. You can check twining genera also here for very simple conjugacy classes and for simple models. And in fact, some of those are giving positive results, so we're doing that, but I can't talk about it here. We can find evidence for moonshine also in models with some of the Wilson lines turned on. I didn't talk about that here. There are results about higher genus curve counts that come from these recursion relations. I did not talk about that here. But even given what I didn't talk about, very many questions remain. And if you care about these questions, you should see the paper that appeared today. Thank you.
So thank you. Do we have any? Hiroshi.
Do you have any idea of what are they that make up a representation of M24?
Well, good. So on the side that has a Calabi-Yau space, it's very tempting to say that since you're counting rational curves or higher genus curves, and since in the limit that I'm discussing there are more or less curves in the K3 fiber, that there's some very explicit degeneracy that could be counted by Gopakumar-Vafa invariants that might also show these representation numbers. That's a very encouraging thing to say. I don't know that it's true, so let me just leave it at that.
Okay. Kommer on. There.
Perhaps I should consult your paper of today, but in case there's a quick answer. So if you take 2,2 theories of these Calabi-Yaus on these FNs, the elliptic genus of them you can compute 0,2. Just generally, they would be invariants of the theory. What would they have any relation to any of the groups?
This is a great question. I don't know. What is true, I think Iguchi, by the way, has done a lot of computations of these elliptic genera for general Calabi-Yau K-folds. But that's a great question, but whatever they would map to, they don't map to the 0,4 elliptic genus in the heterotic theory. So they're not directly related to what I talked about here today.
But nobody tried to connect them to these other sporadic groups.
Like I said, to some extent, Iguchi has results connecting other theories to various groups.
Thank you.
Okay. No more questions. So let's thank the speaker again.